Hello students, welcome to my channel. Please subscribe my channel, press the bell button, press the like button and share it. Today I am going to explain in the current electricity. In that main topics are electric current, conventional current, drift velocity of electron and current, current density, Ohm's law, resistance, resistivity, conductance and conductivity, temperature dependence of resistance, color codes for carbon resistor, series and parallel combination of resistors, EMF and potential difference of a cell, internal resistance of a cell, series and parallel combination of a cells. Now we can see the electric current. The definition of electric current is like this way. The electric current is defined as the charge flowing through any section of the conductor in 1 second. That is I equal to Q by T and I equal to dQ by dt. I equal to Q by T if the rate of flow of charge is steady current. Okay, so if the rate of flow of charge varies with the time, it is also known as a instantaneous current. Now we can see the different types of current. First A, steady current which does not vary with the time. B and C, current whose magnitude varies with the time. D, alternating current whose magnitude varies continuously and direction changes periodically. We can see in the graph A, it is steady current, B and C are the varying current, and D, it is the alternating current. Electricity, the demonstration we can see it now. So here we have used the one battery. In that plastic coated one conductor we have taken. It is connected to the LED. Again it is connected to the positive of the battery. Metals are good conductor of silver, copper and gold. So in current electricity we are using the copper because whose resistivity is very less. Now there is an animated picture, we can see that. So there is an electron, it is moved from negative point of the battery to the positive point. So it is continuously it is moving. So in this way the flow of charge it is moving, no, so it constitutes the electric current. SI unit of charge is coulomb. 1 coulomb equal to 6.25 into 10 to the power of 18 electrons are present. Now we are going to calculate the current. How we are going to calculating the current? That we can see the current equal to Q divided by T. Q is coulomb, T is the second. Coulomb by second, that is coulomb per second is ampere. Now we can see the calculating the, if at 2 second the 5 coulombs are moving, then current equal to 5 coulomb divided by 2 second equal to 2.5 ampere. Conventional current. Conventional current is the current whose direction is along the direction of the motion of positive charge under the action of electric field. Conventional current due to motion of electrons is in the direction opposite to that of motion of electrons. Now we can see the drift velocity and current. Drift velocity is defined as the velocity with which free electrons get drifted towards the positive terminal under the effect of the applied electric field. That is Vd equal to A into tau, or Vd equal to minus bracket small e capital E divided by m into tau, I equal to NEA Vd. Here Vd is the drift velocity, A is the acceleration, tau is the relaxation time, E is the electric field.
Electric current results when charged particles move in one direction. The blue dots represent the charge carriers, of which electrons are the most common. In metals, there are very large numbers of electrons which move easily. Due to the thermal energy of the metal, they dance and vibrate rapidly in all directions. Let's extend this bit of wire, but concentrate only on the electrons we saw in the first place. If we apply a potential difference to the ends of the wires, the electrons will still vibrate randomly, but at the same time they will drift in one direction. It is this drift which is an electric current, and the average speed with which the electrons drift is called the drift velocity. When a current flows in a conductor R, this quantity is calculated in the number per cubic meter, which in metals is a huge number of electrons. If we imagine a piece of wire and magnify it, and that the length of this wire is equal to the average distance travelled by an electron every second. Remember that the current is the quantity of charge that flows past a point every second. And if this length is the distance the charge flows in 1 second, then to work out the current we need to know the quantity of charge in this piece of wire. That total will depend upon the concentration of charge-carrying electrons in the wire and on the volume of the wire. The volume is the cross-sectional area times the length, and the total number of charge carriers will be cross-sectional area times length times n, where n is the number of charge carriers per cubic meter. If the value of each charge carrier is q, the total charge will then be ALNQ. This charge flows past in 1 second, and therefore must be the current I. We defined L as the average distance moved each second. Distance per second is velocity, so L is equal to v, the drift velocity. Just swapping the L for a v, we have the current I equals AVNQ. Rearranging to make v the subject of the equation gives v equals I divided by ANQ. We will use this now to calculate an example drift velocity. Metals have a huge concentration of charge carriers in the form of free electrons. In non-metals, semiconductors and electrolytes, the charge carriers may not be electrons. For example, they may be positive or negative ions or holes in the lattice. But if we continue with copper, with an example of a piece of wire which is 0.5 millimeters in cross-sectional area and carrying a current of 5 amps. Using our equation, the velocity of the electrons will be the current divided by the number of free electrons per cubic meter, multiplied by the charge on each of those, multiplied by the cross-sectional area of the wire. That velocity works out at a snail-like 7.4 times 10 to the minus 4 meters per second. That's less than a millimeter every second. Copper is particularly rich in free electrons. The number of charge carriers in, for example, a semiconductor is far fewer, perhaps 1/millionth. Therefore, to carry a significant current, the drift velocity has to be a lot higher.